So I'd like to start out by talking about first principles of electromechanical energy conversion. And there's a few key points that, in my mind, are defining these first principles. The first one is that the physics of the electromechanical energy conversion are the same for all electric motor types. Basically, what you have is a current multiplied times a flux, giving you a torque, and then that torque is working against a load torque, the torque associated with the losses on the shaft. The resultant summing of that torque is going to result in an acceleration of speed. So when the acceleration of the speed is zero, the electromechanical torque minus the load torque and minus the torque loss is zero. There's always an inertia associated with the acceleration, and then we have a resultant speed. The load torque is the result of some load mechanism and load dynamics. The rotational loss on the shaft is the result of some rotational loss mechanism, say bearings, friction, windage, and the associated dynamics of that. There will also be a rotor position that is the integral of the rotor speed. So this is the same for every type of machine. The second first principle is if there are windings on both the stator and the rotor, they will be transformer coupled across an air gap, and there will be an associated turns ratio. The motor is going to be controlled from either or both the stator and the rotor sides, and it's convenient to transform either the rotor windings to the stator side, which is usually the case, or vice versa. The turns ratio is embedded in the electrical circuit model, so we really don't pay attention to that turns ratio when it comes to the control of a motor. We always work with an equivalent circuit where the terms, the electrical terms that we're interested in, have been referred to one side of these windings or the other. The example is with the DC motor. We have this lambda AF. It's actually the mutual flux linkage between the armature and the field, but it is referred to the armature side of the circuit, which is the rotating side of the circuit. We will see similar type of a model for other types of motor. And as we build up a dynamic model, if we were going to follow the norm for other motor models, for the DC motor model, we would take the field winding and we would analyze it from the rotor side. So even if we wanted to analyze the field winding, as I've been showing us, analyzing it from the stator side or from the field winding side, we would probably just transform everything over to the rotor side. So all of the equations representing the motor are referred to one side, to the rotor or the stator. Principle number 3 is that the spatial derivative of flux linkage applies to all motor types. For example, the DC motor armature is actually an AC circuit. It has a flux that has a self-flux linkage and has a mutual flux linking to stationary magnetic field flux, and that flux varies spatially as the rotor passes by the magnetic poles. So if we apply Faraday's law, we get this expression here. where we have a derivative of the of two terms, the self-flux linkage and the mutual flux linkage. The mutual flux linkage has a theta r, or rotor position dependency. And so if you carry out this derivative, you're going to see the normal L di dt temporal derivative term, but there will also be a derivative of the flux linkage, and that derivative occurs because of spatial variations, the movement of the rotor with respect to time. And we'll use this notation here, the Heaviside P operator instead of the ddt. So we're going to say P is d dt here. Now number 4, because of the DC motor commutator and brush action, we are actually seeing with that machine an AC circuit on the rotor that behaves like a DC circuit. We're also seeing an armature electrical circuit in the rotating reference frame, where commutators and brushes perform a mechanism that constantly reorients the direction of the current flowing through the armature coils as they pass by the stationary magnetic field poles, in order to maintain a quadrature relationship between the armature flux linkage and the field flux linkage. And so what we have, of course, is we have the armature flux linkage oriented 90 degrees away from the field flux linkage. And we're going to assign the axis on which the field is oriented to the d-axis. And then this q-axis, the quadrature axis, is 90 degrees away from it. Now, interestingly, for the DC motor, we can take a look at field flux linkage expression for lambda f. It only has the LF self inductance of the field winding times the field current, and the armature flux linkage is equal to the armature self-inductance times the armature current plus the mutual flux linking the armature to the field. Now, the armature circuit expression we know is this. The armature voltage is equal to the armature resistance times the armature current plus the derivative of the armature flux linkage. So if we plug in this expression, we get this well-known expression that we've been using here. And I'm going to not yet evaluate this, but what we have is we've got a derivative of the mutual flux linking the armature to the field. And I want to focus on that for the moment. So actually the derivative, what we're doing is we're going to be turning a flux linkage into a voltage by taking this derivative. Now, if we look at these axes, it's helpful for us to say, let's find the things we're interested in, the current and the mutual flux linkage, on these axes. And so the current is on the q-axis, and the mutual flux linkage is on the d-axis. So it's it's almost probably the main portion of the field flux linkage would be the mutual flux linking part to the armature. So when we take the derivative of this term right here, what are we actually getting? Well, we can write a derivative this way. The derivative of the flux linkage is equal to J omega R lambda AF. And this is really what I was talking about when I said there's a spatial derivative that occurs with every type of motor. And what that spatial derivative does is it results in a multiplication of the rotor speed times the flux linkage term, but it also results in a 90-degree shift. And so what we've got now on the q-axis is we could represent this entire product here, and we know that this becomes a voltage. It's really the result of Faraday's law, and so this is the EA. And so let's go ahead and write that, and it's now been shifted. We've taken this flux linkage here and shifted it 90 degrees to the left, and it places it right on the q-axis. And so there we have EAF right there. And if we look at this expression here, rewrite it, where everything is lined up on the q-axis. And let's assume we're in the steady state for the moment. This will be 0 in the steady state. Otherwise, there will be some movement. It will be an additional moving phasor that shows up during a transient and then goes away. And then we've got the EAF right here. The sum of these things together are the armature voltage. So let's just add them. So I'm going to select the EAF and put it on the end of the RAIA. And I know I've got a lot going on right here, but what I've done now is by adding these two vectors together, they are going to be equal to VA. Everything in this machine is happening right on the q-axis, and it's unaffected by anything that is happening in the field because of the quadrature relationship. Now, this is the desired behavior of any type of electric machine. Now, I'd like to point out something very interesting. I'm cleaning up this circuit a little bit. What we have is we have this DC motor. Let's look at it from a little different perspective. This is the description of everything that's happening on the armature winding. It's lined up with this axis that we're calling a q-axis, and that q-axis is representing the main torque production of the machine. We've got this other axis, this d-axis, which is 90 degrees out of phase, and we have on that axis the field winding. But everything that's happening is happening on the armature. Now, what's really occurring is that the electrical behavior, what's happening, is all occurring on a rotating structure. So you can think of this circuit as it's moving at an electrical speed of omega sub r. Even though you've got the synchronous frequency, since it's a DC machine, the synchronous frequency we define now as omega E, it's 0, because that's the fundamental frequency of DC. Because of the Lorentz force law, we've got a moving rotor interacting with the field with these armature windings on it, and then the commutator and the brushes are reorienting the coil current through the coils to maintain this quadrature relationship. But everything's happening on the rotor. We can think of it as essentially operating in a rotating frame of reference. That's fundamentally what is happening with a DC motor. So we will come back to this idea and talk about rotational frames of reference with three-phase machines. This takes us to the final and first principle of motor controls. The goal of switching power electronic control of the synchronous induction motor is to achieve electronic commutation, and it makes the motor behave more like a DC motor. So if you recall, when we were looking at the brushless DC motor, we had an exact replacement of the brushes and commutators with power electronic switches. So the brushless DC motor basically is an H-bridge feeding two windings at a time that look like a single armature winding, and then it reorients the switches according to the position of the rotor, the magnetic field on the rotor as it's moving. If we have a sinusoidally wound synchronous or induction motor, and we're supplying it with three-phase pulse width modulations using, say, sine triangle PWM or space vector, where we're controlling the fundamental component of the currents, we aren't going to be able to do what we did with the brushless DC motor. So instead, we are going to really try to mimic the two main things that the DC motor achieves. The first thing is that it is able to control the torque, TE, that electromechanical torque that's applied to the shaft, by directly controlling current magnitude. If we can do that, and going back to the very first of the first principles that I showed you, basically you've got this controllable current. In the DC motor it was IA. That's, if you control that current, then it interacts with lambda AF to produce TE, and then you can compensate for any load torque disturbance, stabilize the torque dynamics, and then direct changes in current are proportional to changes in torque, and the torque is proportional by the inverse of the inertia to the acceleration. So essentially, you just want to directly control current magnitude. Ideally, one current magnitude to achieve this effect. The second thing that you're going to want to do is to control the orientation of the combined MMF. We're dealing with three-phase machines now, of the three-phase stator and, in the case of the induction motor, rotor windings with respect to the position of a magnetic field flux. So we constantly are controlling the orientation. And really that relates to controlling the phase. So I'm going to control the phase. I'm going to control the amplitude. What we're really talking about, as you've heard the name applied to this type of control, vector control. Really controlling a vector for, let's say, the stator current, or a stator current vector, and I will explain to you, give you a little more insight into how this can correlate to three-phase windings. But E, S, E, J, omega, E, T, that's the synchronous frequency that you can control with the inverter. Remember, in the DC machine, omega E is 0, so the synchronous frequency is 0. And but we have this current, and then there's probably some phase that we would want to also control. When you're saying vector control, you're trying to control a vector that looks something like this. Now, I just want you to remember these two main points. We're going to go through some fairly hairy math, and then let's come back to these points. And just keep them in mind that this is what we're trying to do. A good place to start is with the wound field, round rotor, synchronous motor. And I've drawn the structure over here to the right. What we've done is we've moved the field winding to the rotor. We've eliminated the commutator segments, but not the brushes, because we still want to control the field with this machine because it's a wound field machine. So I'm showing the field current is coming in to this machine through the brushes, and then instead of commutators, the synchronous motor will have two slip rings. So you can see this brush that I'm showing right here. That brush there is in contact with this green circle that's representing slip ring. And then we've got another brush riding on another slip ring. Both these slip rings are pressed onto the shaft, and that's the return path for the field current. But we've moved the magnetic field onto the rotor, and then we have three-phase stator windings. The stator windings we've got a phase A winding. So we have stator phase current IAS going into that winding from the inverter supply. We've got a phase B winding and current IBS coming into the winding, the B winding, and then we have a third C winding with the current ICS, stator phase current C, coming into that winding. It's going to be a Y-connected motor, so the other sides of these windings will all be connected together, and this is a neutral internal connection inside the motor. Now what we've done is we've introduced another type of wound field machine. We had spent most of this semester on the DC motor. It has two windings, the armature and the field winding, and now we've gone from two windings and to four windings with the synchronous motor. So we've doubled the number of windings that we have to consider. yet we're trying to achieve the same type of control with the synchronous motor that we had with the DC motor. To start with, let's write the flux equations for these windings. You've got the lambda A, which is going to be equal to, I'm going to write these in matrix form, okay? You can multiply them out just in the interest of time. So we've got a lambda A on the stator, we've got a lambda B on the stator, a lambda C on the stator, and we have a lambda F, which happens to be on the rotor, but I can just leave it a little subscript off of there. And there's going to be an inductance matrix. So we go across rows for each winding. So there's going to be a self-inductance of the A winding. There's going to be a mutual inductance to the B winding and mutual inductance to the C winding. Then we've got the lambda A, the LAF. And these multiply times the currents. IAS, IBS, these have AC content in them, CS, and IF. So we have 4 flux linkages, 1 for each winding. And we can go on with the B. We'll have a B to A inductance, a B self-inductance, a B to C, and a B to F. And we're going to have a C to A C to B, a self-inductance, and then a C to F. And then we're going to have an F to A, an F to B, an F to C, and an F self-inductance. So we've got quite a bit going on here. And let's also, before we explain what we're going to do about that, let's write the voltage equations. So we're going to have a stator voltage equation, and it's going to be the derivative of lambda A stator plus the resistance of the stator. The windings are symmetrical, so they all have the same resistance, R sub S, IAS, VBS, P lambda BS plus RS IBS, VCS, P lambda CS plus RS ICS, and VF, P lambda F plus RF IF. So we've got these 4 voltage equations, and we could write the voltage, these voltages, as a matrix here. We could say I've got a V, this is the voltage matrix, VAS, VBS, VCS, and VF. Now what we need to do is we need to somehow simplify this system. And I'm going to now introduce a way to do that. We're going to recognize a couple of things. Number one, as far as torque producing behavior goes, there is no common mode. We talked about this in the last lecture. So even if we could produce a common mode, it's just going to produce electromagnetic interference. It might cause problems with our bearings and other things like that. but as far as the torque, it's not going to do anything to it. It's the line quantities that affect the torque. So as a result, we can say that, well, remember that we're using only the fundamental components of the voltages and currents, the AC voltages and currents. So any high frequency and any harmonics that we are producing by our power electronics, we're ignoring that. And our goal is to basically average out to produce average AC voltages to give us average AC currents. So basically our goal was to have the inverter produce VAS equals VS, that's the peak phase voltage, cosine, and now we're producing synchronous frequency with our inverter. So this is theta S. VBS is VS cosine theta S minus 2 pi thirds. VCS is VS cosine of theta S plus 2 pi thirds. So one of the key things that I can control to control the armature behavior is this one amplitude, Vs. And if I can make my controls and the way I look at the motor correlate to, in a very more simple way to that, it's going to help a lot. So we've got those two things, and then because of this, if even these three voltages, the way they're described here, essentially these are the fundamental components of what the inverter produces. They have VAS1 plus the VBS1 plus VCS1 at any instant of time will sum to 0. So that tells me that one of these windings, the behavior on one winding, is going to be dependent on the other two. So for example, VCS is equal to negative VAS1 minus VBS1. So I've got only the third main point here is I have two independent stator windings. So I really only have 3 windings. So there's going to be 3 lambdas and 3 voltage equations. So how do we go from 3 stator windings to 2 stator windings? And I'm going to explain one way to go about this. Let's remember that we could also express any phase voltage as a phasor. So for example, we know that VAS is equal to some amplitude VS cosine omega E T where omega E is the electrical frequency and it's also equal to the synchronous frequency, which is omega S. And as a phasor, we can represent this term VAS here as being derived from a phasor by taking VAS equals to the real component of this phasor, VS EJ omega T. If you recall from Euler's expression, EJ omega T is the cosine of omega T. So let's put this down as, let's start, so since omega S and omega E are equal, we'll use omega S here. Omega S plus J sine omega S of T. So the real component of that is the cosine. But this is the phasor. And so what a phasor looks like is a rotating vector. And this is the expression here, and this is representing that phasor superimposed on two quadrature axes. And I'm going to name these axes. We're going to use two different standards for naming them. One of them is the alpha axis, and I'm just going to put the name by the positive side. Remember that if this is positive side, then there would be positive values reflected onto this angle and negative values reflected onto the other angle, the other axis. You could also call this same axis the stationary q-axis. So I want to not to confuse this sub s, so it's a superscript s here. It's not the same as synchronous. It means stationary. And usually when those who do research in this area or who have taught in this area, if they're going to use this notation here, they'll often refer to synchronous as by the E. Say E is synchronous. The textbook doesn't do this. The textbook just uses omega s and it uses alpha. But it's helpful to understand that this alpha axis is really could be considered a q axis that's stationary. And then you've got another quadrature axis called a beta axis, or it could be referred to as a stationary d axis. And so this phasor it reflects on all three axes. And likewise, we could represent B, state or phase of B, as being equal to Vs, as being equal to the real component of Vs, Ej omega St times e to the negative j 2 pi thirds. So it's phase displaced by 120 degrees, negative 120 degrees. And then the stator C voltage, the real component of Vs, Ej omega St, E positive j 2 pi thirds. And so each one of these three phases can reflect onto these two stationary axes. This is very related to the approach I was showing you for how I came up with how space vector PWM is done and reflecting a phasor onto three phase axes. So it's kind of the same idea. And it's really in a mathematical artifact here that we're using to our advantage. Okay, so if I've got this situation, I can use various approaches to come up with a mathematical way of reflecting onto two axes, but I'm going to use a very general way that's going to be helpful to us. Basically, how do you transform three phases to two phases? So one mathematical expression I'm going to give you is going to give us the behavior I was explaining up here. So how I'm going to do it is I'm going to come up with a general expression for any electrical quantity. And then this expression could apply to the voltages, it can apply to currents, and it could apply to flux linkages. And so we're going to basically say any one of these three things here is being represented by F in this expression. And so I have an F sub Q, and I'm going to put a little n up here, which this represents the frame of reference. So a general frame of reference. And I'm going to have an F superscript N D. And I'm also going to have a third one. I'm just going to show this once, where this is a 0. So I've got essentially a QD0. Some people swap the D and the Q and call it a DQ0. But we're going to stick with QD0 because that is what's used in machines. This is equal to some matrix, which we're going to call a rotational transformation, and referred to as T theta, where theta equals 0 for n equal s, stationary, theta equals theta s for n equal e, which is synchronous frame, or theta equal theta r for n equal r, which is the rotating frame. So you have stationary, synchronous, or rotating. And then this matrix is going to multiply times whatever the quantity that we want to transform, the A phase, the B phase, and the C phase. So, for example, we're talking at this point about F sub A being equal to V A of the stator, V sub AS. So the transformational matrix is this. First of all, there's a multiplier on the outside. There's different approaches that people take to using this multiplier. I use this one. And then the top row of the matrix is cosine of theta, cosine theta minus 2 pi thirds, cosine theta plus 2 pi thirds. Then the second row is sine of theta, sine theta minus 2 pi thirds, and sine theta plus 2 pi thirds. And then the third row, don't ask me why this is used, but it's 1 over square root of 2 is the standard notation. Now the third row is really the common mode, represents the common mode. So this represents the, if there is any common mode, it's there. But as we've already stated, since, and now we'll just say in general, FA plus FB plus FC equals 0, there's no common mode. which means that f sub 0 would be 0. And that's what we'll be assuming, and is what we have to assume if we're going to go from 3 phases to 2 phases. So cleaning things up and substituting in for this arbitrary f, we're going to find the VQ of the stator phase and a VD of a stator phase, and there's a V0 of a stator phase. We're going to basically say there's no common mode, so this is 0. Therefore, this entire row can be ignored. And we've assumed now that theta is 0. So we have these 0 terms here. So what we actually have is we now have a 3-phase voltages, 3-phase stator voltages, and these could even be 3-phase stator voltage expressions, converting them to 2-phase stator voltages. And as we stated before, when I was introducing this phasor reflecting on to 2 axes, V alpha is equal to VQSS. V beta is equal to VDSS. So the most common approach is to use the V alpha and the V beta. And then this would be equal to times, so the cosine of 0 is 1. The cosine of negative 2 pi thirds is negative 1/2. And the cosine of positive 2 pi thirds is negative 1/2. The sine of 0 is 0. The sine of negative 2 pi thirds is negative square root of 3 over 2. And the sine, this should be a positive 2 pi over thirds is square root of 3 over 2. Times the 3 voltages, VAS, VBS, and VCS. And so we're going to multiply these things through. And I'm going to stick with just the alpha and the beta here and come up with an expression for V alpha and V beta. Now these two expressions simplify down into two expressions that actually have a well-known name called the Clark's equation. So these are the this is the Clark equations. Now there's one other point about these Clark's equations. They actually simplify down even more, and they're actually well used in drive controls in developing the software for performing these transformations in real time. And the reason they're used is because they're very computationally efficient. But let's just look at the V alpha for just a moment. Let's assume that VAS is equal to V cosine of, we'll just say theta S, and VBS cosine theta S minus 2 pi thirds, and VCS VS cosine. I bet there's a more mathematically elegant way for me to explain this, but if we assume that this is true and we plug these into here, what we're going to get is something very interesting. It will help us to apply a trig identity here. So this is Vs cosine theta s cosine 2 pi thirds plus sine theta sine 2 pi thirds. And then the VCS is a similar expression, except that there's a negative sign. So we're actually going to plug these expressions in here. And what we end up getting is V alpha. So it's we've got 2/3 times the Vs cosine theta s. Now these two terms here are summing. So if you sum these two terms, then obviously these are going to cancel out. And so we're going to get the sum of these two. It's going to subtract off 2 times Vs cosine theta cosine 2 pi thirds divided by 3. And simplifying that even further, this is minus 1/2, and so that's going to cancel out this 2. And it's going to become a positive, so we're going to have plus Vs cosine theta over 3. So what's very interesting is that we've actually got Vs cosine of theta s is that's V alpha, and that is VAS. So the Clark's equations simplify even more. And this, you can carry this through for any quantity, and you're going to get the same thing. If it was current you're looking at, you'll get the same type of expression. So we can generalize this and rewrite the Clark's equations. It doesn't state that that's what they're called, but this equation is found in the textbook on page 214. So this is equation 5.126 and 5.127 in Krishnan. We're kind of going all over the map as far as where the book is covering these details, because frankly, if we were going to teach this exactly right from the textbook, it'd probably take 2 semesters to get through it. And so this is what the equations are. We get V alpha is equal to VAS, and V beta is equal to VCS minus VBS over square root of 3. So those are the Clark's equations. And very important. Well, you may, if you go into the drives industry, you probably hear this mentioned, this equation a lot, and now you know where it came from. I want to go a little bit further, and let's consider the addition of 2 axes that are rotating now at the synchronous frequency. So I'm going to introduce a stator Q axis in the synchronous that's basically rotating. So it's let me highlight these to point this out. That axis, that's the Q axis, and this axis, which is the D axis. And I purposely offset them from the phasor here, because the phasor doesn't have to be on any of these axes, but what's happening is the phasor is also rotating at the same frequency as the axis, so they're rotating together. And this is your theta s, it will define the theta s as its the difference between the q-axis and the alpha axis. And we're going to get another set of equations called Park's equations. So you hear people talk about Park's, Clark's equation. The DSP for my drive does Park and Clark. Well, what it's doing is it's rotating things into these. It's eventually going to put the voltages or currents into a reference frame that's rotating at either the synchronous frequency or the rotor frequency if the rotor frequency is different, say if it's an induction motor. So let's take them and let's say that we're going to convert from the alpha beta to the Q and the D. We're going to say that we've got a VQS in the synchronous frame, VDS in the synchronous frame, and that's equal to cosine of theta s, because this is the angle that we're using. We're considering a synchronous machine, and sine of theta s, sine theta s minus cosine theta s times, say we were starting with the alpha beta, we could just say times V alpha, V beta, whatever we have for that. Same thing if we were using the VQS in the stationary frame, VDS in the stationary frame. Multiply it times the same matrix. So there you have Park's equations. Another important point I like to make is that you could get the same result without going in a two-step process. So basically go from three-phase to two-phase in the synchronous. And I want to point out that it could be synchronous or it could be, we'll say, rotating reference frames. So it would apply in either case. So what I mean by that is that if we're going to the synchronous reference frame, we're going to use theta s. If we're going into the rotating reference frame, we're going to use theta r. Now, if it's a synchronous motor, which is what we're talking about, theta s equals theta r. So you could use these interchangeably. If it's an induction motor, theta s does not equal theta r because of the slip. So there's a slight difference. And in induction motors, you often want to use the rotating reference frame, the rotor reference frame. Anyways, bottom line is that we could have gone directly from the three-phase to the synchronous or rotating frames in this way, where we have VQSE, VDSE being equal to 2/3 times that full matrix. I'll just use the theta s here right now. Okay, so that's how you do it. You don't have to go, you can do it this way, or you can do Clark's equations going from VABC to VQD synchronous or state or stationary frame, and then as that be a step 1 and then a step 2, Park's equations going from, actually, so I said this was V, I'll put in parentheses V alpha beta, going from VQ, so these are, depends on preference, VQDS or V alpha beta to VQD in the synchronous frame. So why do we go through this instead of the other one? Well, I mean, this is easier to remember. So this is what I use whenever I'm talking about it, because I don't have Clark and Park equations memorized, but this is much more computationally efficient. Computationally efficient. So there you have it. Now, what the point is that what can we do with this? So I know that we've been through a lot since we started this lecture, and yet have we really said much? Well, I think now we've got to bring it all together. So we have, remember that we're talking about the synchronous motor. So this was the synchronous motor. With a wound field. And these were the differential equations that we came up with. And we had even started the lecture going back ad nauseum through the DC motor and looking at the differential equations there and really kind of focusing on, the flux linkages. The whole issue with these three-phase AC machines, it's not the complexity of these voltage expressions, but it's the complexity of the flux linkages that really makes things difficult to, say, even mathematically model in simulation, much less figure out a good way to do controls for it. So what we can do is, because we've now come up with this expression here, and we've got this transformational matrix T of theta S, that we can go from the three-phase to the two-phase synchronous. We can actually simplify the model. So what you can do is you can say, let's just take these three voltages, but it's really the expressions that they're equal to here, and plug those in here, and then do the math. Now the math is quite involved, and it's not really worth our time to go through it. I've got a resource up on Canvas that does it. There's a great book by someone by the name of P.C. Krauss that really explains this well, and I can't remember the title off the top of my head. But anyways, the end result is that we are going to come up with a much simpler set of equations. So we started with having 4 windings here because we have 3-phase windings, and we've got that field winding on the rotor, and we're going to get them down to 3 because we're going to knock down the number of stator windings to 2. And we're going to have all of our expressions now written in the synchronous reference frame. And so this is what the voltage equations end up becoming in the synchronous reference frame for the synchronous motor. And if you want to understand where everything I'm talking about is coming from, go to chapter 9. See, we're really going all over the map here of Krishna's book. Okay, so in chapter 9, we get VQS is equal to, I'm going to write these expressions a little bit differently. In the book, it talks about so if we go to the starting with this resistance, stator resistance, it has a Q and a D stator resistance. It says RQ and RD, but in reality, they're not going to be any different. They're still going to be RS in both the windings. So those, they won't change. I'm going to use RS times, because we've converted in the process of doing this mathematical conversion, not only have we converted the voltages into this synchronous DQ or QD reference frame, but we've also converted the currents. So we have a current. We've got the derivative of the flux linkage now. Instead of it being we had an A winding, a D, and a C, we've got a Q stator flux linkage winding that is in the synchronous reference frame. So we've also ended up converting the currents and the voltages, everything into this frame. And then we have this back EMF term, lambda ds. And we have a D axis winding voltage. So we've ended up with, we had Q and D current voltages. We've also got Q and D currents and Q and D fluxes. Now this is the most interesting and fascinating thing about doing this transformation. Focus on these two things here. So this is your coming from Faraday's law, your spatial derivative terms. Notice that you have a Q circuit. Everything is in the Q, except we get something from the D axis. The flux in the D axis goes into the Q. And then if we go on to the D equations, the flux from the Q axis goes into the D. So these are what's often called cross-coupling between D and Q. So what's very interesting is the flux linkage expressions. You see how complex they were before. We're really going to get these down into much simpler expressions. So what we end up with is we really only need to know 2 flux linkages for these voltages here. We've got the Q Q winding flux linkage in the synchronous frame will be equal to some inductance called the Q-axis inductance. Now in this case, the inductances can be very different, or they could be the same. It depends on the structure of the machine. So you have LQ times IQS, and that's it. Now the D-axis is going to be LD IDS plus a mutual inductance from the field winding IF. And to be complete, we could add the field voltage equation. So the field is on the rotor. The rotor is rotating in the synchronous reference frame. And so really, we didn't have to do any transformation. We're already there, and this equation didn't change. So it ends up being RF times IF plus P lambda F. And the lambda F doesn't change either. And the lambda F becomes a different expression also, because if you look at what we had here, we had the couplings from all these other windings here. And in this case, the only winding that couples to the field winding is the D-axis. So we're going to have a lambda F equal to the self-inductance times the field current plus a mutual inductance times IDSE. Now what I had made the point before about how we're going to be looking at all of we're looking at everything from a stator or rotor perspective. So this is different from rotational transformation. It really has to do with turns transformations. So what I've done is I've assumed everything is reflected to the stator windings. I don't have any primes or anything else. Just accept that. It's reflecting them doesn't mean this is just what has happened to my inductance values in particular. Now what this really means is the LD breaks out into a leakage inductance in the D-axis plus the mutual inductance. The LQ is a leakage inductance in the Q-axis, and there is a mutual inductance, but for this simple synchronous motor that we're considering, we don't have any Q-axis coupling. Otherwise, this LM might be important. We don't see any of this happening in the DC motor, by the way. This is something that happens with the sinusoidally wound machines. And then the LF is the leakage of the field winding plus LM. This would be like an LMQ, and this is like an LMD. So these aren't all the same. Another point is that if you have a round rotor, which is what we had assumed, LD is equal to LQ. If you have a salient rotor, then LD is not equal to LQ. They're going to be different by some variation. We don't have time in the class to go into
ground versus salient. That's something you can delve into if you're interested. Another point I will make is this, that you have in a synchronous motor, you must line up theta s exactly with the line, with the line voltages. What I'm really talking about here is, here's your, say, your Vs e to the j omega t, and you've got there is a voltage that is really related to to this term right here. So that's the omega r lambda ds. We've got our q-axis and our d-axis here that's rotating. This is rotating here. There is a difference between these two voltages. This is very much like your V armature in your DC motor. This is very much like your back EMF in your DC motor. The angles of these have to be lined up according to LS and RS. Otherwise, you're going to be basically locking up the motor. So the synchronous motor absolutely must know the position. It must know the position of lambda d in particular, okay, which will be can be easily found from rotor position, because theta r equals theta s. Okay, so this is a kind of a complex point, but what did people do before they had vector controlled drives and things like that that can achieve this type of capability? There were actually additional windings, two more windings. So you in a wound field synchronous motor, and these were called, they're typically referred to as damper, or I think the word is amortisor windings. Basically, and I'm going to show this as if we had a salient pole, two-pole wound field. We've got all the turns. This is your field current here. What they would do is they would add bars, just almost like in an induction motor, across the poles, pole faces. And they actually might even add some in here too. And these would become your damper bars or windings, similar to a squirrel cage machine. So these actually would stabilize and allow a line start of a synchronous motor without a drive. That's what they had to do back in the day before power electronics. And so if you actually see something in the book and you're wondering about that, that's what they're talking about. Now, there's a final point that needs to be made, but I'm out of time, and we're going to make that point in class the next time we meet. This has been a bit of a tough lecture for me to prepare to try to just, I'm trying to cram all this background information into your heads. You're really not going to see why it's so important until our next lecture. And then I'm going to give you the final point that you need to know and show you how to connect it up with the induction motor. And then we'll leave it at that, because this is really for the benefit of your projects. And my intention is to only give you a small homework that I'll issue this next week to kind of solidify your mind on a few of these points. I don't want everybody to stress over it either. The main thing is I want you to be able to do your projects. I want you to learn from the class. And so anyway, that's it. Thank you.